So we end by discussing why this is all called linear least squares. Some equivalent statements. We want to find the best solution x hat that approximately solves ax equals b. We've seen that this is the same as finding x hat such that a times x hat is the orthogonal projection of b onto the column space of A. Now it turns out that that's also the same as minimizing the length of b minus ax. What does that mean? Let's go back to our animation. This point that z points to is the point closest to the point. What do we have here? We have the vector b that is written as the sum of z plus w. Now, when the point that z points to is as close to the point that b points to as possible, the vector w is as short as possible. So that justifies this statement right here, because a times x hat is that vector z. Now, if you look at that, and then you look at b minus y, but you square it, then you notice that you're trying to minimize the difference of these two vectors, which then is the same as minimizing the square of the length of the vector that is the difference. And that's the same as minimizing the sum of the squares of these components of the difference. Now, that's probably easier to figure out if you look at this picture right here. We saw that the points on the line have y coordinates equal to the vector that is the projection onto the column space of A. Each of these terms here is this difference right here. So what we're doing is we're summing the squares of these differences, and then we try to minimize that. And the line that minimizes that is the line that comes from solving the linear least squares problem.